Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And is about to start as a postdoc at MSR New York. So it contains convex analysis in the title, and so I don't want that to scare you. It turns out you actually only need to know 2 facts from convex analysis, and so I'm going to give them to you in the first 2 slides, and that'll be more than enough to understand through the talk. So the first thing you need to know is basically the idea. So if you have a convex function, right, a function whose epigraph, the set of points above it, is the convex set, then if you take a derivative of it and plot a line out along that derivative, it's always going to be below the function, so like this x here. And more generally, even at points where the function may not be differentiable, that just means you have a whole family of these tangent lines you can choose from. And each of them will still remain below the function. We call each of these a subgradient. That would be the gradient if it exists at a given point, if the function is differentiable there. So that's one fact about convex analysis. The second is a way of constructing convex functions. And so the important thing to know here is here I have in the dashed lines 3 different convex functions. And I've created a new function by taking the pointwise supremum, by just taking whatever of them had the highest value at that point. And in doing so, I created a new function that's guaranteed to be a convex function. So that's it. That's all the convex analysis that you're going to need. Are there any questions so far? Okay, good. So we've had a number of talks over the past day and a half or so that have touched on mechanism design. So I'm going to treat it very generally. So there's going to be some set of outcomes in the world. Say, for example, we have to pick whether we should spend a bunch of money to build a new bridge or to make a nice park. And then lots of people may have different opinions about how much they like this. So you might find someone who values the bridge at $5. Maybe they have to cross the river quite a bit. And then they might value the park at only $3 in terms of how much they would personally be willing to pay to have it. So in general, you can think of the private information that a person might have, or their type, as a function that for each outcome associates a real number with it, which is how much that outcome would be worth to them. And so I use functions here because that turns out to be the correct mathematical thing you want to use for the convex analysis. You could also just think of this as a vector that reports the value for each outcome, and and that's going to be entirely equivalent if everything is finite. So we've assumed that we have some agent in the world who has private information, and now we're actually going to have to make some sort of decision. So we're going to have some function that's going to take the type of the agent, and it's going to pick one of the outcomes for our set. For example, a very natural thing you could do is you could just go through and pick the outcome that's going to make the agent the happiest among all those possibilities, right? That's a perfectly natural thing you could do. So that's one function that shows up in mechanism design. The other function that shows up in mechanism design is a payment rule that says, okay, now also based on that information, I'm going to decide how much you have to pay. And you could, for example, do what would be a first price auction, and that is charge them whatever they said the thing that you chose was worth. And then once you've chosen these 2 things, then they have some utility. And their utility depends on both their true type, because they care about the outcome that gets selected, and it also depends on a type that they reported to you. So their utility, if they make some bid B and their true type is T, well, it's the value that they receive for the outcome that's chosen. So with this rule, he said that the bridge was worth 2 and the park was worth 1. So the bridge will be chosen. So his value from the outcome chosen is going to be 5. And then his payment says he pays whatever he said it was worth. So he said it was worth 2. And so his overall utility is going to be 3. Now, one note about this utility function that will turn out to be important later is that this utility function is an affine function of his true type. You see a term here that's a function application. If you like thinking of types as a vector, this is just a dot product. So this term is going to be linear in the true type. And then there's this payment where the true type doesn't appear at all, so it's just a constant from that perspective. So in terms of your true type, this is an affine function. And then if you want to talk about, well, is this mechanism truthful or not, truthfulness is just a property that says your utility for making any bid is less than or equal to the utility you get if your bid was your true type. And so in this in this setting, we see actually that this mechanism is not truthful, because if instead of bidding 2 and 1, he had bid his true type, well, the same thing would be chosen, but now he's going to pay 5, and so his utility would have been 0. So this design turned out not to be truthful. So are there any questions so far about kind of what mechanism design is, or how I've represented it for the people that know mechanism design? Okay, good. And so then there is quite a bit of theory trying to answer the question of, well, okay, we saw that one mechanism we came up with isn't a truthful mechanism. What are all of the truthful mechanisms that we could use? And so Myerson, in a paper that did quite a few major things in it, but one of them was he answered this question for what are known as single parameter domains. And you can think of these as domains where the private information is just a single number, like how much do I, if there's only one item being sold, how much do I value that one item? And he showed in that setting a pair of an allocation rule and a payment rule is truthful if and only if the allocation rule is monotone. That is, if your type is higher, if you have a higher value for whatever it is, you'll get more of it or be more likely to get it. So monotone in that sense. And then there's a particular way of constructing what the payment rule has to be from the allocation rule. So we kind of gave this nice if and only if characterization. So that's for single parameter domains. It turns out to be exactly equivalent to say that the consumer surplus function, that is basically how happy you are, the utility function before, how happy you are given both the outcome and the amount that you had to pay, if that is a convex function and at any given point the allocation that's given to your type is a subgradient of the convex function at that point. This turns out to be an entirely equivalent thing to say, and if you want to know why, it turns out that basically going on here, you have an integral of this function a. We assumed a is monotone, and the integral of a monotone function is a convex function. So if you want to know why they're equivalent, that's why. The main thing that's important for the talk is that they are equivalent, and this is actually true more generally. So Myerson's proof about a monotone allocation rule is only true in kind of limited settings, but this characterization that involving a convex function and its subgradient is true in general. Okay, so now I'm going to switch to an entirely different domain, but also a domain where people care about truth. So again, there's going to be some set of outcomes, and the outcomes here might be whether it's going to be rainy tomorrow or whether it's going to be sunny tomorrow. And now instead of having a person who has preferences over which of those outcomes happens, although these are probably things that we have preferences over, there's someone who has some information about how likely these are going to be. For example, there might be a weatherman and who has some probability distribution over how likely these two things are. And this being England, maybe there's a probability 0.1 of sun and a probability 0.9 of rain. And now we would like to have the expert who knows this information reveal it to us. So we'd like to come up with some rule that, based on a report that we're going to ask for from this expert and an observation of what weather actually arrived on tomorrow or whenever we're interested about, we want to give that expert a score. And so, the score could be, for example, well, there's a typo there. It should be QO, not PO. But the score could be, for example, the payment you get is the logarithm of the probability with which you said the outcome that actually occurred would have occurred. So it could be, any rule, and this is the payment. This is the rule by which we're actually going to pay you to give you an incentive to truthfully reveal the information that you have. And so, well, what do you as the expert care about then? Well, you're going to get, your payment is, well, some outcome is going to be realized according to a true distribution that you know, and then you're going to get scored based on this rule you've been told. So that's your expected score, and note that because expectations are kind of a linear operator, this is in fact affine and in fact linear in your true information. So maybe this is what the world looks like from the perspective of the expert. That's one potential scoring rule. And so again, we care about truthfulness. We want to ask, well, does this rule we wrote down have the property that the best thing the expert can do is to reveal his true probability distribution? And it turns out it does, and you can show that in fact the score for any other thing is going to be less than or equal to the score for the expected score from reporting truthfully. So this is an area where I care about truthfulness. Looks in many ways quite different from mechanism design. So another place that has almost up to a minus sign the same definition is machine learning, where you might care about proper loss functions, which is a loss function that guarantees that if you knew the true prediction you should be making, the loss function would actually be minimized by that. It's the exact same question. Questions so far? Okay. So there's been quite a bit of work on this scoring rules literature, and in fact there's a very nice characterization theorem that actually goes back to the 60s in its original form, but stated kind of in a nice general and modern version by Gneiting and Raftery, and they showed that a scoring rule is proper if it's derived in this particular way from a convex function and the subgradients of that convex function. All right, so we have a different, so far we've seen kind of two different sort of domains where we care about some notion of truthfulness. We've seen kind of two different characterization theorems that were kind of proved entirely separately. But they have, quite a bit in common. There's sort of some sort of outcomes about in the world. There's some sort of affine function being computed that's what we care about, and there's kind of a notion of truthfulness that looks syntactically similar. So what's going on? Why are convex functions that are subgradients showing up in both of these? And the answer is that second fact that I told you before, right? Truthfulness is a property that says the supremum over all reports I could make is equal to the value that I realize given my true report, right? That has to weakly dominate everything else I could do. Well, we know that then if we view this value of what do I get with my true report as just a function of my true report, because of this construction we saw where we're taking a pointwise supremum over affine functions, which are convex, the resulting g we get from doing that is going to be a convex function. So that's why really in general in these different domains where we care about truthfulness, what's popping out of it is a convex function. So the main thing we do in our paper, which is available on arXiv and has the same title of this talk if people are interested in seeing more of the details that I'm going to give, is we write down kind of a general model that encompasses both mechanism design and scoring rules, as well as sort of any of these other settings that kind of have this property where you're trying to get something truthful. And so basically all that we care about is that there's some set of types that's going to be a subset of a vector space, a reward space that's going to be based off of affine functions, and then some way of selecting based on the type of the agent one of these affine functions. And then truthfulness, a notion of truthfulness that I've kind of written in a curried notation here. You can think of it as a parameterized family of functions if you prefer, because remember that the types here are functions themselves. And kind of the main result we have from the paper is a characterization of basically what all of the things you can do that are truthful are in any of these settings. And certainly this is for the most part known in both mechanism design and scoring rules already. So kind of this idea isn't wholly new in and of itself. There's certainly bits and pieces we get that are new from the unification we're going to present. So in fact, if you look at this here, and then we go back a few slides and look at the Gneiting and Raftery characterization theorem, right? The two equations are very similar, and it's not going to be an accident. The major thing, to say is that, well, basically we say that truthfulness consists of picking some convex function and then a selection of its subgradients, and it's an if and only if characterization. So why is this the way we get truthfulness? And so I have a picture that has quite a bit going on, but hopefully I can walk you through it and give you a sense of why these things are showing up when we care about truthfulness. And this picture may be somewhat familiar to people who know good about scoring rules. So here we have the convex function g, which you can think of as, if I am of some type t, what is my utility going to be? And in mechanism design, this is the consumer surplus function, but this is, in general, the expected utility I'm going to have if I report truthfully, right? And now, okay, so now consider me being this particular type t. Well, I could make any other report. I could report anything in here, and I would get maybe this blue function for that report, which, because the mechanism I've chosen is truthful, has to coincide with g at t and has to be below it otherwise. And so the question is, well, where do these other points on it come from? Well, suppose I had instead chosen to report some t prime. Well, what does this scoring say that I get for reporting t prime? Well, I'm going to start at g of t prime, so I'm going to start at this point, and then I'm going to walk out along a subgradient essentially from t prime to t. So what I'm going to do is I'm going to walk down to there, and so you'll notice that that is exactly the value of the blue function at a report of t prime. So that's where that point is coming from. And so why is this giving us the truthfulness property that we want since we picked a convex function? Well, the definition of being a subgradient is a linear function tangent to the point and always below because we have a convex function. So that property, sort of definitionally, being a subgradient is exactly that property we want of being always below, and is why truthfulness is coming out and is giving us our if and only if characterization. So it's late. I won't go through the details of the proof. I will say that the proof is very familiar to people who know scoring rules. The first two slides are exactly lifted from Gneiting and Raftery's proof. So there's literally nothing new in the first 2/3 of the proof. There's a little bit here that involves letting us handle handle settings where the set of types may not be convex. But even that actually borrows heavily from some work in the mechanism design literature by Archer and Kleinberg. But the 3 slides I clicked through fairly quickly are literally the entire proof. And if I had a little more time and it was earlier in the day, I would actually go through them. So it's not actually a hard result to prove by any means. It's actually really simple. But it's nice because in pulling together kind of this characterization, that looks a lot like the one used in the scoring rules literature, but also brings in mechanism design, we can then immediately start taking results that are known in one literature and applying them in the other. So for example, mechanism design, had considered and figured out what mechanisms could look like with non-convex type spaces, because maybe it might be perfectly reasonable to believe that I might not have all possible combinations of values, might not be sensible in some setting. And so this maps directly over into the scoring rules, and we now have a characterization that didn't exist before of what scoring rules look like in non-convex settings. And why is this interesting? Well, you might be thinking, okay, I'm going to ask a weather forecaster to report me some probability, but in reality, people don't have arbitrarily fine, real-valued beliefs about probabilities of events in their heads. And if you're going to want to have a nice, simple elicitation thing, you might want to discretize it in some way. For example, if you want to apply these in a more general setting of maybe evaluating reports people are going to make in a crowdsourcing system, you may well want to discretize the reports you're going to allow people to make. And so there's a question, okay, if I go through and do this discretization, is this going to have any effect on the incentive properties, or am I going to get more or fewer things I can do? And one of the things that comes out of our characterization is actually this discretization is entirely irrelevant. It doesn't change. As long as you don't change the convex hull of the set of types, you aren't going to change the things that are truthful at all. Perhaps less of general interest that allows us to relax an assumption that was needed in the mechanism design literature in one of the characterization theorems. So those are things that are immediate from just the characterization theorem. Another thing that we can do from this view of the world is actually go through a large literature in mechanism design and greatly simplify it and give both conceptually clearer proofs and a better understanding of how these things fit together in several ways. So one thing that people have been interested in mechanism design quite a bit is the following question. So I have a mechanism consists of 2 parts. It consists of an allocation rule and a payment rule. And so there's some settings where I care about that payment rule, maybe as I want to be collecting money, but in other settings I just want to be using this mechanism to optimize some desirable outcome in the face of rational people. I don't really particularly care about the money other than that it's helping me get a good outcome. So then the question is, what are all of the different allocation rules, all the way of choosing outcomes that I can implement truthfully via some payment scheme? I don't care what payment scheme it is, but some payment scheme, and get something truthful out. And there's a large literature that have looked at various aspects of this. So the Myerson argument I mentioned earlier shows that essentially the property of being an implementable allocation rule is equivalent to being the subgradient of a convex function. And so there's a paper from the 70s by Roche that identified a different equivalence to a technical condition known as cyclic monotonicity that actually comes out of convex analysis and is very heavily connected with the property of being a subgradient of a convex function. And then there's been a bunch of other work. I think this was from much of it sort of since 2007 or so, finding weaker or more local conditions that are useful for providing this characterization. But all of them sort of go back and work with this cyclic monotonicity condition, which is a really nasty thing. And and other than these, I only know of a single example where anyone has ever successfully derived a mechanism and proved it truthful using cyclic monotonicity. Pretty much every other setting, it's a very unnatural thing to work with. So instead, actually, we argue that you should rethink this whole literature and think of all of these arguments as, instead of looking at cyclic monotonicity, arguing directly that some set of properties is equivalent to the property of being the subgradient of a convex function. And this allows us to give dramatically simpler proofs as a number of these. So for example, this is one condition I picked out from the literature because it's particularly nice. They identified two properties that lead an allocation rule to be truthful, or in our sense, a selection of subgradients to be a selection of affine of linear functions to be subgradients of a convex function, and that is they satisfy a technical condition called weak monotonicity that you don't really need to understand, that I'm not going to go into, other than that it's sort of the right generalization of the monotonicity we saw in that one-dimensional setting before. It's the right generalization of that to multiple dimensions, and a path independence property that basically says if you start going, it's basically says this is a conservative vector field, if you know what that is, but basically if you start doing integrals along through this space of linear functions that we've chosen, it means you get path independence. Basically, if you take the integral from point A to point B and the path integral from point B to point C, then that's the same as having taken the integral from A to C. And so they establish as the main result of, it takes them about 12 pages, and it's the main result of a GEB paper, so it's a fairly strong paper, and they put really a lot of work into proving this fact. If you view the world through the approach that we're using, it actually turns out to be a single slide and about the level of difficulty you could give to an undergraduate as a homework assignment to do the proof. Because it essentially just proceeds from first principles. The only slightly tricky thing is we need to find the right definition of a convex function G. But once we define that convex function G, it's a matter of proving this function we've constructed is convex from kind of the standard first principles. You take an x and a y, and you take some linear combination of them, and then you just argue exactly that linear combination is greater than or equal to the value of the function at that point. The standard textbook way of proving a function is convex, and you apply weak monotonicity, and you apply path independence at the obvious places in the algebra, and the answer pops right out. So sort of as an analytic tool, this approach gives a dramatically simpler way to approach these sort of problems. And actually, one of the nice things is that it's not just simple to prove these, but it's also more constructive. Because in that proof, I said the first thing we did was went and started out by constructing explicitly a convex function G, and through explicitly constructing that convex function, we explicitly construct the payment rule. So as a result, we know not just that there exists some set of payments that make this allocation rule truthful, but we have a very natural way of characterizing exactly what those payments are in a lot of settings. And actually, we think that, so basically this literature had been going on by people focused on mechanism design, but what we show is they had effectively been proving new necessary and sufficient conditions for being the subgradient of a convex function. So we actually think that, sort of using our theorem to pull the results the other way, we actually think, I don't want to say this, I'm not a convex analysis person myself, so I don't want to say it too strongly, but I have talked to a couple, and as far as I know, actually, several of these characterizations are not generally known in convex analysis in terms of necessary and sufficient conditions for being the subgradient of a convex function in one setting or another. So I think actually this creates some new results in convex analysis. And for example, for people who care about Turing rules, this lets us say that, for example, it turns out to be sufficient to consider local misreports in the scoring rule space. So this was kind of known in mechanism design, but you don't actually have to check if a scoring rule is proper for arbitrary misreports. It suffices to check for sufficiently nearby reports. And so, in everything I've talked about so far, we've wanted to take kind of the full private information that an agent has and elicit that. But in a lot of settings, that's not really natural. So, for example, suppose I wanted to ask, a person, please tell me your entire probability distribution over the quantity of rain we're going to get in the next month, right? Expressing that probability distribution is, you can give me find an arbitrary PDF or an arbitrary CDF or something like that, but there's this whole space of nasty functions, and I mean, if I'm going to, do this on a computer, I have to give them an interface that lets them construct arbitrary PDFs, right? It's kind of an unnatural thing, and I may not care about actually the whole richness of this distribution, even if they could, bring their beliefs down into such a complex thing. I might actually only care about something like the mean of this distribution or some other statistic, right? Or, for people from more of a mechanism design background, there are lots of settings where maybe I actually, particularly in settings where I don't want to use actual money, maybe I only care about people's preference order over the outcomes. And this shows up in mechanisms that are used, for example, in matching problems like matching medical residents to hospital residency slots or matching students to schools and those sorts of problems. It turns out the mechanisms don't ask for the utility for each outcome. They just ask for some sort of preference ordering over the outcomes, right? So there's sort of these settings on both sides where you care about this kind of indirect elicitation of the private information of some kind of intuitively simpler representation rather than eliciting the actual thing. It turns out you can formalize this into this notion of a property of the type you're interested in, and there's a little more complexity, but you can generalize our main theorem to be able to handle all of these cases. So actually, not just do we carry these kind of what would be direct revelation mechanisms in the mechanism design sense, but we also actually characterize all of these other more indirect things that are useful for settings where you don't want to deal with the complexity of the full type space. And you can observe sort of a number of interesting and useful things from this characterization. So one thing that follows immediately, for example, is that because convex functions are differentiable almost everywhere, and it turns out that our characterization says that canonically asking people for a property means you're asking them to pick a subgradient for you. So it turns out that if a property is elicitable, it has a unique value almost everywhere. Because for some statistics, there may be multiple values that are equally reasonable as the true value. So actually this fact lets you rule out some things as not being elicitable without doing any further work. So it kind of gives you a tool to show that things are not elicitable. It also has several other nice things that I think I won't go into. There are a bunch of other applications of this that we do in the paper. For those that know revenue equivalence and mechanism design, it turns out that it's sort of you can prove revenue equivalence theorems for various settings using this approach. I went through kind of two main areas where we care about truthfulness, but there's been a literature of kind of other variants of scoring rules. For example, where you want to get counterfactual predictions. So you want to ask somebody to predict what would happen if I did something. Then you may or may not do that. So you may or not be able to evaluate that prediction. Well, what do sort of scoring rule-like things look like in that setting? All of these things kind of have the affine property. So instead of people having to go and prove a new characterization theorem each time you want to ask kind of these variant questions, we have this one characterization theorem that covers all of them. And one I want to talk a little bit about is Robert's theorem. So in particular, I've cheated a little bit so far on the mechanism design side. And in everything I did, I only had a single agent in the world. And that wasn't an accident. Because in one sense, that's all that matters, because if you look at any notion you care about, like Bayesian incentive compatibility or dominant strategy incentive compatibility, they all essentially look like something where you can project down onto a single agent. So for example, general truthfulness in dominant strategies says, for all strategies, for all types of other agents, I want this truthfulness to hold. So you can check if something is truthful by just looking at each of those projections individually and verifying each of them. And sometimes this sort of characterization is enough to do something really useful. So for example, this was exactly the characterization Myerson used for single parameter domains. That's led to a lot of very practical mechanism designs, because it turns out to be good enough to there are many practical cases where you can show the thing you care about is monotone for once you've fixed other people, and so that works great. But there are also a lot of cases where you really want to be able to say something stronger about what happens with multiple agents, and those sorts of characterizations have been harder to come by. So one really well-known example is Robert's theorem, which says that if you have a setting like the example with the bridge in the park, but there are at least 3 outcomes, and there are unrestricted valuations. That is, every agent can have any possible value for each outcome. You're not going to put any sort of other constraints on how the values have to be related. Then there's only one mechanism, sort of one family of mechanisms you can do that's going to be truthful for all of the agents simultaneously, and that's what's known as an affine maximizer. And basically what that is you're going to compute a value for each possible outcome that consists of an arbitrary constant you associate with that outcome, and then a weight you associate with each agent. And so you sort of score the outcome by summing over all agents their weighted value for that outcome, and then add the constant for that outcome and call that the value for that outcome. And then you take the outcome that maximizes that. And so those turn out to be the only allocation rules that are truthfully implementable. And there's been a lot of hard work trying to relax this unrestricted valuations thing, because this rules out things like combinatorial auctions, for example, where there are natural restrictions, such as the idea that, well, if you give me an extra thing, that can only increase my value because I still have all of the things I had before. So there've been some work that's managed to stretch it a little bit in this direction. But one thing we're kind of working on as future work is we think there's a way to use our characterization to give both a simpler proof of Robert's theorem, which I guess the proof is short and not too hard to verify, but a lot of people find extremely hard to understand why on earth it works. And so we think we can kind of give a bit of a simpler, more intuitive proof, and also a proof that we think we see how to generalize towards this. So that's kind of future work and what we're working on at the moment. So to wrap up, we have our main result is a kind of a new characterization of truthfulness that generalizes both scoring rules and mechanism design. And it gives us simpler kind of constructive proofs about what allocation rules are implementable. And while I didn't talk about it much in this talk, we can generalize it to these sorts of indirect elicitation settings where we only care about, say, some property of a distribution. So thank you.